Thank you, Barbara and Patrick, for organizing this workshop, and thanks for the organization. So you see here two dancers. They are doing something which is called contact improvisation. And how it works is that they dance, they improvise following their context. How they rely on feedbacks between them, so you never know what's going to happen. And for instance, on this picture, it's difficult to know who is driving the other. And it's because of these feedbacks. And I think that for the lithosphere and for the mantle, it's the same thing. We have dynamic feedbacks between them. And it's often useless to try to say the lithosphere, the plates are driving the flow, or the mantle, or the mantle is driving the plates. It's often useless to talk about causality in such a complex system. So we'll try to talk about this. So dynamic feedbacks between the interior of the mantle and the tectonics at the surface. It's a collaborative work with a group of Zurich. We use here the mantle convection code that they develop, STAG-YY, and we work with the Earth-by group to be a little bit more grounded to Earth when you are into the models. And in Lyon, we develop inverse methods to try to connect them. So when we talk about mantle flow, we are a bit like Alice wanting to go to Wonderland. It's not an easy task. You have to drink a lot of this magic potion because we don't have a lot of information about mantle flow. So we use, some people like us will use models to try to have ideas about the mantle flow. So the hypothesis I'm going to use right now to try to use as a single system, to try to study as a single system the lithosphere, the plates in a way, and the mantle, is to use the same physics for the lithosphere and the mantle. And so this hypothesis, in fact, I'm not the only one to make it, since you see here a calculation by Boris Kos, for instance. But many people working on lithosphere dynamics use the same kind of equations that we use for mantle convection. So we reach a point there, we sort of use the same kind of tools. So I'll go in that direction. So one some specifics of lithosphere deformation with this kind of tools is the lithosphere needs to be able to handle some stress. So when the strength of the lithosphere is strong enough, is high enough, then the lithosphere can handle the stress. But when you reach some special stress, then you cannot handle the lithosphere cannot handle the stress, and then there is a localization of the deformation, and this is where you have shear localization, and it's the fundamental aspects of lithosphere deformation. So we have to have that into the models, and it's quite difficult. So the equations I was talking about are these ones. There are a few assumptions in these equations. So here, U is the velocity, P is the pressure. You have the Rayleigh number, RA, T is the temperature, C the composition, R is a parameter for buoyancy related to the composition, Q are the heat sources, and I guess that's it, T is time. So we use these equations, and they use these equations as well. So there is no compressibility here. Lots of things are approximated. But when you solve these equations, the collective behavior, the global behavior, cannot be easily predicted. It's a complex system, so we know every rules at the local scale, but we don't know what will emerge at the global scale. A fundamental parameter for studying the coupling between, not the coupling, the global system, lithosphere and mantle, is the viscosity term that you see here. And we have lots of problems about this. We have difficulties to know what are the the deformation mechanisms, especially at low temperature, low and high stress. So it's difficult for us to use experimental values, but Philippe Carrez will talk about that more tomorrow with lots of new things, which are very interesting. So we need to go to a plan B to estimate the viscosity. This plan B is to estimate this viscosity laws empirically. Try to find what empirical laws will give you a regime of Mantle convection and tectonics that seems, at least at first order, consistent with the Earth. So Paul Taclay, but other people worked a lot on this. What do we need to do to get to a sort of plate tectonic-like behavior in a global convective regime? And the three main things that people will use are first the high activation energy for the viscosity, which means that at low temperature the material will be very, very viscous. So you will have a sort of a rigidity at the surface, which is the fundamental for plates. However, if you just have very, very viscous rocks at the surface, they will never yield, and you will have a planet with a lid at the surface, which is not the Earth. So you need to sort of yield the lid, and people use pseudo-plastic approximation to do that. So one way is to use a yield stress, which means that when the stress in your flow reaches the yield stress, then the viscosity drops to accommodate this stress, and the strain rate increases a lot. And with that, you obtain some shear localization. Then a third thing that people use that enhance the plate-like behavior is to have some sort of super solidus weakening, which means that below the boundary layer, you have some sort of low viscosity region, which helps to have a plate-like behavior. So like Mark Richards has some work also on that. So when you work a lot on these parameters, you find some regimes that have some sort of plate-like behavior. And I'll show you a calculation, some results right now, just to show you how what it looks like. So this is the surface of one model, and I'll show you it's about 150 million years of integration in time. So the color is the viscosity. When it's red, it's very viscous. So when it's red, it looks like plate. You have some more reddish zones at north and south. These are continental rafts that are imposed in the models. So they are imposed in a very crude way because continents deform, but here they are very stiff, very viscous. What you see in blue on this snapshot are regions where there is a yielding at the surface. So this yielding, there's no history in this yielding. There are a lot of approximation. It's more empirical than anything else, but still we do that. So these blue regions are low viscosity regions. They are like some sort of plate boundaries. They are not imposed here. They just emerge from the temperature field and the interaction, the equations I showed you before. It's an emergent phenomena. It's not prescribed. So what I show you here is going to be a reorganization of the flow. So you start with a triple junction at the south. On the west side, you have a subduction zone that is moving. The continent in the north is going down, and the continent in the south going up. You have also a subduction zone changing on the north. And you see here the ridge system that is evolving thanks to the reorganization on the other side. You have a subduction zone that is going north, towards the continent, the west side, and you arrive here at whoops, sorry. Stop here. So you get to a new situation where you have changed the ridge system. A ridge is almost connected to the continent on the north. You see this continent in the north is almost rotating. So this is the kind of behavior you observe. New subduction zones, they are moving, retreating. So when they retreat, all the ridge systems are changing. So you observe that. If you look at the interior of the model, so it's the same model right here. What you see are two isotherms. The red one is just a hot isotherm, so you can see plumes. And the blue one, forget about the viscosity thing. The sort of blue one is to see downwellings, to see sort of subductions. And what is in yellow are the stiff continents. So in this lifetime, you see plumes quickly reaching the surface. Sometimes some of them are dying. Well, it's tough to see to describe quickly some things right here. But so you see very fast plumes, and you see you can follow the subduction zones that you saw in the first movie. What can be interesting here is to see, for instance, you have a sort of window in the subduction system in the north. Right here, when I showed you before, the ridge was connecting to the subduction zone, and then you open this region, for instance, which is you open inside the slab a sort of window. So this is the large-scale flow that we have in this kind of models. The flow is large-scale. I'm going to talk to you about this a little later. But you have also a smaller-scale flow, and this is a bit difficult movie to watch. But what you see here is an isotherm behind at the bottom of the boundary layer at the surface. And you look it from like if you were lying at the top of the core. So you see what I mean? So it's just to see what you see here in the middle is the big ridge system in the middle of the calculation I showed you before. And there are some red stuff, which are the top of the plumes that are just cut so we can see well. So you have here 1, 2, 3, 4, 5, 6, 7, 8 plumes here on this big plate. And you see this small scale convection, which is occurring at the base of the plate. So this is a consequence of the dynamic feedback as well, which means that since you have stiff plates, they can only yield when you reach a certain stress. So you can have some plates that don't yield, but are still unstable relative to the stability of the flow. So you have instabilities that can develop at the bottom of the plates before you reach a yielding criteria, and you subduct. So I just show you. So these instabilities, they start after a certain time. You see that close to the ridge, the isotherm is quite flat, so there is no instability. The instability takes time to develop, and when it gets unstable, it develops, and until it goes to the subduction zone. So here you see a capture of one of the plumes at a ridge. And you see the motion of these instabilities. They generate a flow within the upper mantle, because the viscosity in the upper mantle here is lower than the lower mantle. And the kind of structure of the flow it generates there are two different interesting structures for the flow. One is in the wake of plumes. So for this big one here, sorry, you see this plume here. You see that there is a wake behind it. So the effect of a plume is to rejuvenate, in fact, the seafloor. So the seafloor behind the plume is less unstable. So you generate some sort of channels behind the plumes, which are interesting maybe for some interpretation of the seismic tomography of channels behind the plate. And the length scale here of these small scale instabilities are here in this model about 200 kilometers. This is the kind of flow that it generates. If you are below a slow plate, the drops are just sinking almost vertically. So it's kind of circular flow. And if you go fast, the flow is different. It reminds me some work by Thorsten and Claudio in mountains, below mountains. You know, this kind of flow. But this kind of flow also is interesting when you look at, I guess, anisotropy or this kind of things. So now I have two possibilities to finish my work, my talk, and maybe I guess I'll try an interactive choice because I won't have time to talk about everything. So I can explain you the dynamic feedback that leads to the explanation of the size of plates, this thing that you may have seen already. And I did a sort of tentative forecast experiment, which is a failure, but maybe interesting failure, where I try to generate a flow when not pushing the plates and getting to compare it to the tectonics at the surface we see today. So who's for the plate size? Nobody? The plate size or the tentative forecast experiment, the failure experiment, trying to reproduce the tectonics at the surface without imposing plate motions. Second? Okay. So you want to see my failure. Yeah, maybe. So it's a tentative forecast experiment. So the goal here is to, because we've worked a lot on the parameterization of the models, trying to see, understanding some of the feedbacks between the lithosphere and the mantle. We can adjust some parameters so we can have some sort of decent size distribution of plates and some other things in the convective system. And the goal is to see if we can make some predictions with it. Predict doesn't mean explain. So the way I do it is I try to generate some initial conditions for the model. I don't know what was the temperature field in the past. So I start from an arbitrary initial condition, almost arbitrary. I tried many. And then I push the plates at the surface of the model. I impose the plate reconstruction from 200 million years to 50 million years. So I push, imposing a sort of structure of the flow. So I start from there, and I get to this point here. So here actually it's pushing until today. So you see isotherms like I showed you before. And from this stage at 50 million years ago, I just let the model compute the forecast. Don't impose anything anymore. Try to see the flow. That can I predict the surface tectonics doing that from these initial conditions? So I don't. So this is the state at 50 million years. So this is not pushing the plates. These are the motions, the surface velocities and the viscosity at the surface of the model predicted by the calculation. So what you see here, the viscosity. So when it's high viscosity, it's like plates. When it's low viscosity, it's like plate boundaries. So the plate boundaries look a little bit like what we expect for the Earth. Most of the ridges are fine. the smaller plates close to the east side is where you have the more problems. You see that you predict India is moving fast towards the Eurasia, and so it's not so. The prediction is not so wrong yet. After 20 million years, India is reaching Eurasia. The African continent here is moving quite fast towards Eurasia. And on the west side of the North America here has not really moved a lot. And especially it doesn't really move the right way here. So the opening of the South Atlantic Ocean is okay, but not for the North Atlantic. At 10 million years, Australia is still connected to Antarctica, so it seems there is sort of rift system between them, but not enough to split them, so they are both going north. Africa and Asia, they don't move too much anymore because they are kind of collided against Eurasia. And it's still for North America, there is something clearly wrong because the North Atlantic here is closing. But on the east side, you still have the sort of ring of fire, this sort of subduction system on the east side of Asia, and a little bit on North America and South America. And this is the prediction for today. I think it's useless to show you the plate velocities for today because it's sufficiently off. But what can we learn from this? The first, as a modeler, I'm happy just to be able to, at the end of the calculation, get some, how can I say, like a coherency of the calculation. Like after 50 million years, the behavior of the system is not off compared to the Earth. The plate boundaries, the plate velocities are quite far, but still I still have plates. They still have some correlation to the plates we started from. So this is quite for me at least. It shows me that the parameterization is not completely off. The second thing is that we make errors here. So we have the errors can come from the parameterization of the model, so model errors. The error can come from also initial conditions. So how can we make the difference between both? I guess here it's very difficult to make the difference, to see the difference. For the parameterization, the fact that we keep a sort of coherent system, that we can make connection of tectonic events that happen in this system and happen on Earth, tells me that at least in the parameterization, a lot of things are fine. For the initial conditions, there are some problems I can identify too, especially for North America. So the initial conditions was the temperature field at 50 million years. And in this temperature field, the difficulty is when you push the plates in these models, we don't regularize the plates like some teams they do. And the way plates are going, the way the surface is, the cold boundary layer is pushed inside the system, make sometimes some sort of drops or some break-offs within the sort of slabs. And also there are some artificial stresses that you have when you do that, which has been documented. So in fact, what happened, why the North America has moved, I can explain that from this problem, because when I start the free run, I start it when the slab is breaking off. So there's almost no, the forces acting on North America here are really not realistic from these initial conditions. So I guess having questions is more interesting. So just to say that to correct for initial conditions, you've seen already some work by Peter, and making some inversion would be important to correct for that. And maybe then we will be able to correct for the parameters if we can. Thank you.
Thank you.